Okay, so we are now recording. All right, so before we start class, does anybody have any questions about life, the universe, or anything in general? You guys never have any questions when I ask about that. Okay, well, let's just go ahead and get started on last night's homework then. Okay, so what is the photoelectric problem? All right, well, hopefully you guys understand that it was this one right here. So with classical waves, with the kind of waves that people were always used to prior to light waves, there's two ways that you could increase the energy that the wave delivers to something. Okay, one way is to increase the frequency of the wave, so the more waves per second hit. Okay, so that obviously would work. And the other way that works with a classical wave is to increase the amplitude of each wave. And when scientists tried to do that with light, they found out that no matter how bright they made the light, it had no effect on the energy of the electrons that they had, and that's how they were measuring the energy of the light was by exciting the electrons. And so they found that no matter how bright they made the light, it had no effect whatsoever on the energy of the electrons, and that totally baffled them. It was a huge problem in science. Until Einstein came along and said, well, maybe light is not a classical wave. Maybe it's a quantized wave. Okay. All right. So why is that so important? Well, because that opened up the door to quantum mechanics. That was the first time that people realized that maybe waves are not what we think they are. And so that opened up the door to quantum mechanics, and that totally changed the world. I mean, if it wasn't for quantum mechanics, you and I would not be talking right now online, because quantum mechanics is the key to is one of the keys to how computers work. And in fact, on Friday, we're going to talk some more specifically about that. How exactly is it that your computer depends on quantum mechanics in order to work? But we'll save that for Friday. Okay, so if you want to use a parallel plate electron gun, okay, to give an electron the same amount of energy that a green photon has, 530 nanometers, okay? So I hope that you guys got this one okay. Here is the way that I did it, okay? So I started off with E equals HF, which is an equation that you are going to be using a lot, so make sure that you know it. But because we don't know the frequency of the light, I'm going to replace F with C over lambda. So E equals HC over lambda. Okay, we know what H is. That's a number that you should use that. By now, you should have used that number so much that you have it memorized. 6.63 times 10 to the negative 34. That's Planck's constant. Okay, so I plug in the numbers and I get this number of joules. Okay, but I'm not done yet. What I need to do now is I say, okay, so if I've got an electron gun, so the energy of the electron is going to be Q times delta V. So just do a little bit of algebra to figure out what delta V is. Take the E that I got from up here and stick it in down here. And bingo, we get 2.3 volts. Okay. All right. Now, did anybody get confused when you were reading the book prior to doing the homework? When you got to page 727, okay, yes, with all in capital letters. Okay, let's take a minute and talk. Okay, yeah, it hurt my brain. Okay, so here's the deal. So E equals HF is the formula that works with standard physics units. So what the book did was they took H and C and kind of multiplied them together, and they adjusted the exponent to account for lambda being in nanometers. And so what they did was they said, okay, we're going to take each E equals HF, and we're going to change it so that when you plug in lambda, instead of plugging in 530 times 10 to the negative 9, you just plug in 530. Okay, so if you put lambda in nanometers, so in this case it would be 530, then just take 1240 and divide it by that, and then that'll tell you the energy. But, and now this is really important, the energy that it tells you will not be in joules. The energy will be in electron volts. Okay, so let's try that. Let's take the Book's equation. Let's take 1240 and let's divide it by 530. Not 530 times 10 to the negative 9, but just regular old 530. Okay, so if we do that, guess what number we get? We get 2.34, which is the exact same voltage that we got before. Okay, so the Book's way of doing it will tell you how many electron volts a photon has if the photon has a wavelength of 530 nanometers. Now, I do not recommend that you try to memorize the Book's formula. I would say the best way to do it is use E equals HF. That is a much more easy to remember formula, and it'll be less confusing. Okay, so just remember E equals HF, or HC over lambda if you prefer it in that form. And so I would say go ahead and take the 530 and put it in as 530 nanometers, and recognize that the E that you get is going to be in joules. And if you need it in electron volts, well, then go ahead and convert it into electron volts. And yeah, it's a few extra steps than it would be if you use the Book's form, but it's a way that is easily understandable. Okay, so that's what I recommend that you do. Okay, hang on just one sec. I'm still working on this camera thing, trying to figure out a way. I think I probably should just give up on it, but I'm trying one thing. Give me a sec to try one thing. No, it's not. It does not seem to want to work. Okay, well, I guess I'll give up on the video. Okay. All right, so let's move on. Can you use the Book's way? Sure, absolutely, for sure. You can use the Book's way. I have no problem with that. Just make sure that you understand what's going on. Okay, so let's get back on to this one. So question number 3, we want to use a parallel plate gun to give an electron the same amount of energy as the photon. Well, if the energy on the plates was 2.3 volts, then that means that the electron's energy is going to be 2.3 electron volts. And that's why the electron volt is such a useful thing. In circumstance like this, when you're having electron guns and you want to give them a certain amount of energy, whatever the voltage on the gun is, just that's how many electron volts of energy it's going to have. So electron volts actually are a pretty useful thing. So Josh is asking, what was the momentum equation in the reading last night for? Actually, we're going to talk about that. Hold on to that, Josh. We are definitely going to talk about that today. Okay. So question number 4. So if the work function of some metal is 3.1 electron volts, okay, so which of these various colors is going to be able to eject electrons? Okay. All right. So the way that I approach that is I say, okay, if the work function is 3.1 electron volts, let's convert that into joules, because we know that 1.6 times 10 to the 19 joules is equal to 1 electron volt. Okay, so now we figured out how many joules it is. So then we can use E equals HF to figure out what is the wavelength of a photon that has that same amount of energy. Okay, so it works out to be 401 nanometers. Okay, now here's a case where if we had used the Book's special formula, the one that we just talked about, it would have been faster and easier to use that. But in this case, I'd say, let's not worry about it. I prefer to just work with E equals HF. Okay, so how much energy will the electrons have if instead of shining violet light on it, you shine green light on it? Okay. Now this was not one of the quiz questions. This is just a follow-on question that I want to ask you right now. Okay. So let's suppose that we've got some metal, and we figure out that 400 nanometers is the wavelength of light that just barely has enough energy to kick an electron free. So if instead of shining violet light on it, if instead we shine green light on it, then how much energy are the electrons going to have? Well, I hope you guys realize that's a trick question, okay? Because green light has a lower frequency, therefore it has less energy. Therefore, it doesn't have enough energy to kick the electrons free. So if we take this metal here and we shine green light on it, we're not going to get any electrons out. Okay, there's a certain threshold of energy that you have to have in order to kick electrons free. If you don't have at least that much energy, no electrons are going to come out. Okay, and the secret word was, of course, Zawarudo. All right, so here are the answers to last night's homework problems, at least the ones you haven't already looked up in the back of the book. Does anybody have any questions about them? Okay, can we do number 2? We can definitely do it, and number 4 also. We can do that one as well. Okay. Oh, hang on just a second. My book is out of reach. Hold on while I go grab the book. Okay, yeah, I should have put the book a little closer here. Okay, so question number 2. Okay. All right, so number 2 is saying what's the energy in electron volts of an electron with a velocity of 6.2 times 10 to the 6th. Okay, so what we need to do is we need to find out how many joules of energy that is. Okay, so let me try something here that I haven't tried before. Let me try. Okay, so you guys know that the kinetic energy of an electron is 1/2 mv squared. Okay, that's pretty bad, right? Okay, so if we know the mass of the electron and we know the velocity of the electron, we can figure out how much energy it has. Now, what units is that going to be? That's going to be in joules. Okay, so we need to convert that to electron volts. So however many joules that needs to be, that's going to be in joules. So what we need to do then is we need to say that so 1 electron volt is 1.6 times 10 to the negative 19 joules. Well, that's really terrible. But you do that and you should get the right answer. Okay, so Emmanuel, does that answer your question on number 2? Okay, question number 4. Okay, let's talk about that. So the stopping potential for if a cell is 5.7 volts. So we want to know the maximum kinetic energy of the electrons of the emitted photoelectrons in electron volts. Okay. Yeah, that one's worded a little bit weird. But basically, what they're saying is that if let's see, I wish I had a picture to kind of show you. Okay, so here's the metal. Okay, so we got electrons coming out. Here's the other plate right here. Okay, so if it takes 5.7 volts to stop that electron, what that means is that that electron has an energy that's equal to 5.7 electron volts. Okay, we could calculate it in joules if we wanted, but they asked for it in electron volts. And so here, this is why electron volts are such great things, is if we measure the energy of those electrons in electron volts, then whatever the voltage is, that's the stopping potential, that is the number of electron volts of energy that they have. So Maddie, I hope that answers your question for number 4. I'm going to go on to number 6 then. Okay, good. I'm glad to see it does. Okay, so the threshold wavelength of zinc is 310 nanometers. Find the threshold frequency in hertz. Well, okay, that I hope is you guys will agree is really easy. Let me see if I can erase all these things. Is there a quick and easy way to erase these? There's got to be a way to erase the annotation. Hang on. Oh, okay, here we go. Okay, clear all the drawings. Okay, so which one are we doing now? We're on number 6. Okay, so if we know the threshold wavelength and we want to hold the frequency, well, that's easy. Frequency is just the wavelength. Oops, sorry. Frequency is just C over the wavelength. Okay, all right, so that's I would hope you agree that one's trivial. Okay, so then the work function, okay, well, the work function is however much energy that is. So the work function is equal to H times the threshold frequency. Okay, so if we calculate the threshold frequency, then just stick it in there, and that'll give you the work function. Okay. Now that's going to be in joules, okay, and they said they wanted in electron volts. Okay, so that's fine. So then we know the 1 electron volt is 1.6 times 10 to the negative 19 joules, and voila, we're good there. Okay, so Tabitha, does that do it for you on problem number 6? I'm going to assume that it does. Okay, good. All right, so let's clear all that. Okay, and then the last one you wanted was number 8. Okay, so we got a metal that's illuminated with 193 radiation, and the electrons of 3.5 EVs are emitted, so what's the work function? Okay, so we need to know how much energy does does a photon have if it's 193? So here I'm going to use the formula that the book gave that I told you guys not to use, but it is such there are times when it's easier. Okay, so they're saying that the energy is equal to 1240 divided by the wavelength, but the wavelength has to be in nanometers. Okay, all right. So what we're going to do is we're going to take 193, going to stick it into there. Okay, and then that will tell us what is the energy of the photon in electron volts. So I'm typing that into my calculator. Okay, so I'm getting 6.4. So that's how many electron volts of energy the photon has. Now, could I have done that another way? Could I have done that by saying E equals HF? Yes, but then that would have been the number of joules. So then I would have had to convert that to electron volts. But I could do that, and I'd get the same answer either way. All right? Okay, but that's the energy of the photon. Okay, so remember, some of that photon gets used up in the work function, and the rest of that energy is left over for the electrons. Okay, so what they're telling us is that the electrons that come out have 3.5 EVs of energy. So whatever 6.4 minus 3.5 is, that will then tell us how much the work function is. So if you do the math there, you're going to find out the work function is 2.9 electron volts. Does that answer your question there, Josh? Okay. All right. Okay, good. So let me clear all that away. Okay, having a touch screen is real nice. Boy, if I tried to do that using the mouse, that would have been terrible. Okay, well then I am going to assume that we're good with the homework if I don't see any more questions. And let's move on to the new stuff. Okay. All right, so just a little bit of quick review. Some of the very important works on quantum mechanics. Okay, so there are 3 things that are vitally important. One is Thomas Young's double slit experiment. And we've talked about this at length, so I'm going to trust you guys are good on it. So basically, prior to Thomas Young coming along, pretty much everybody agreed that light was a particle. And then along comes Thomas Young and proves that, oh, it's not a particle, it's a wave. And his argument was irrefutable. So everybody says, okay, light's a wave. And everybody was happy until they discovered the photoelectric problem. And so they said, well, something's going on that we don't understand. I mean, light's a wave, but it's not behaving like a classical wave. What's the deal? Okay. So everybody was quite perplexed about that until along comes Albert Einstein, and he says, well, maybe it's not a classical wave, maybe it's a quantized wave. Okay. All right. So then now we get into some new stuff. Okay. Along comes a guy named Louis de Broglie, and he does a bunch of work with electrons that opened up a whole new window into what physics is. Okay, so let's take a minute here and let's talk about what Louis de Broglie did. Okay, first, hopefully you guys understand. So, well, let's go back and let's talk about Thomas Young. So if you look at the light coming in the window here, you see that the shadow here has very sharp edges. And so this is one of the reasons why people were convinced that light could not be a wave. Because if it was a wave, you should have diffraction and you shouldn't have sharp edges like this. You shouldn't be able to see all these little lines like that. And so people said, see, light's not a wave. But then Thomas Young proved that it was a wave. So how do we explain why the light has sharp edges? What's the reason why it is that when you shine a light through a window, it doesn't diffract, or at least we don't notice the diffraction? Well, the answer is because, and it's not because it's fast. That, nice guess. Yeah, but why is the diffraction so small? Jaron, yes, that's exactly it. Okay, so the reason why is because the wavelength is so small. It's way smaller than anybody ever anticipated. Everybody figured, well, if light is a wave, it's going to have a wavelength that's similar to the kind of waves that we're familiar with, water waves and sound waves. Okay, and those wavelengths are really big compared to a window. And so, yeah, you would certainly get diffraction. It never occurred to them that the wavelength might be so small that you have to measure it in nanometers. So you guys hopefully remember that if the wavelength is tremendously smaller than the opening, then the amount of diffraction that you get is so small that it's not easily noticeable. Okay, so if Thomas Young had done his double slit experiment using openings here that were the size of a regular window, you would not get this diffraction pattern. What you would get is you get a bunch of light coming in and hitting right here, a bunch more light coming in and hitting there. The only way you can get this diffraction pattern is if you use really small openings, okay, where the openings are somewhere on the order of the wavelength. Actually, if the opening is smaller than the wavelength, that's when it works the best. But as long as you're somewhere in the neighborhood of the wavelength, that's it. So that's why Thomas Young was able to see the double slit, the diffraction or the interference pattern, was because he made the opening small. Okay, so now let's get on to Louis de Broglie. So Louis de Broglie, he got the crazy idea to try Thomas Young's experiment, but instead of shining a light through the double slit, he said, what would happen if I shine electrons through the double slit? Okay. All right. So so he's got an electron gun that's shooting a whole bunch of electrons. Okay. And he takes the same kind of slit, the same size slit that Thomas Young had used, and he shoots electrons through the slits, and what he sees is exactly what you would expect if you threw a bunch of marbles through the window. And which, by the way, is the same thing that you would see if you shined light through a normal size window. You would not see a diffraction pattern. What you see is that all of the light goes through this window and you get a bright spot right here, and all the light goes through this window, you get a bright spot right there. You do not get a diffraction pattern, okay? And so nobody was surprised when Louis de Broglie did this and he got this type of effect, because of course electrons are particles, right? You guys all learned back in junior high school, electrons are like little marbles, right? And the proton is a bigger marble, right? That's what you learned back in junior high school. Aha, okay. So Jaron is saying, well, maybe we've got the same thing going on here that we did with Thomas Young. What would happen if we make the slits even smaller still? Okay, remember these are pretty small slits here. Thomas Young had to use small slits in order for this to work. Okay, so so Jaron is wondering, is there a way that we can make the slits really, really, really small? And it turns out that there is. It's not easy, but it is. It is possible. If instead of using a traditional type of slit, if you use a crystal as your diffraction grating, okay? So think of, you call up Mr. Ramsey and say, hey, Mr. Ramsey, you got lots of crystals. Can I borrow one of your crystals? Can I shave it down really, really thin and shine electrons through it? And when you do that, all of a sudden, guess what you see? You see a diffraction pattern, okay? So this was mind-blowing. And here, I really regret not having my camera working, because if my camera was working right now, what I would do is I would hold up my, in fact, tell you what, let's do it, because this is really important here. So oh, even my rear camera's not working now. I think I'm gonna have to reboot my computer. Okay, well, anyway, so imagine that I'm holding my hands up next to my forehead, one hand on the right hand side, one hand on the left side, and then I go, and I make the exploding motion with my hands, because that's what's happening here. This is mind-blowing. When Louis de Broglie shone light through his super, super small crystals, okay, he got a diffraction pattern. So let's think about what that means. This is exactly the way that we proved that light was a wave. This experiment right here is the way that Thomas Young proved, without any doubt, that light is not a particle, it's a wave. So if Louis de Broglie is getting the same thing with electrons, what does that mean about electrons? Sorry, Joshua. So those of you who are watching the recording, you can't see the comments here. What Joshua just typed in was, he said, please don't tell me that electrons are waves. Well, I got bad news for you, Joshua. Electrons are waves. And it turns out that it's not just electrons. Protons do the same thing. You can do the same experiment with protons and basically any type of a particle. So it turns out that the entire world, the entire universe, is actually made of waves. Yes, Jaron is right. Everything has a wavelength. Okay, so the universe that we live in is very, very, very different from what we supposed that it was. So yes, Kiker, even we are made of waves. Your entire body is made of waves. This sounds like string theory is what Hiram is saying. And yes, we are going to talk about string theory. String theory is a little different, but related. Okay, but I'm not going to talk about string theory today. Let's learn how to walk before we try to learn how to run. Okay, so just in case you're wondering how it is that a crystal could be used as a diffraction grating, there are various types of crystals. If you take iron or chromium or other types of things, it's going to have a crystal structure like this. Aluminum or copper or gold has a crystal structure like this. These guys would be kind of hard to use, but if you take a sodium crystal, it has a really nice structure that it lends itself very well to being used as a diffraction grating. So when Louis de Broglie was using when he was doing his experiment, what he did was he shined light through a crystal like this. I don't know if it was salt that he used, but it could have been. It was certainly a crystal like this. And it was only when he got to the really small wavelengths that he was able to see it, because it turns out that the wavelength of an electron is super, super, super small, way even smaller than the light. Okay, so here's a picture that you guys hopefully remember. We used this picture when we did the lab where we measured the wavelength of the different lasers. You know, we had the blue, green, and the red lasers. And so what you guys, when you did the lab, was you measured the distance from the diffraction grating to the wall. You measured the distance between the central bright spot and the first diffracted bright spot. You did a bunch of simple mathematics and you were able to figure out what the wavelength of the light was. Well, you can do the exact same thing with electrons. So you can figure out what the wavelength of the electron is. Now, the interesting thing, well, one of many interesting things that Louis de Broglie discovered when he did this was that the wavelength turned out to be inversely proportional to the velocity of the electron. Because you guys know that you can shoot electrons at pretty much any speed that you want. We've done so much work now with electron guns that you guys know that by varying the voltage on the electron gun, you can give the electron whatever velocity you want. And so what Louis de Broglie did was he shot electrons through here, and he started off at slow speed, and then he increased the speed and then increased it some more. And what he found was that the wavelength was inversely proportional to the velocity. So the faster the electron went, the shorter the wavelength turned out to be. Now, as I said a minute ago, electrons aren't the only things you can do this with. You can take protons and shoot them just as well. You can modify your electron gun to make it so that it shoots protons, okay? And protons have a different mass than the electron does. And you can also shoot other types of ions as well. So Louis de Broglie did that. And what he found was that if you increase the mass, that also decreased the wavelength. Okay, so we got that the wavelength is inversely proportional to velocity, and it's also inversely proportional to mass. So what we can do is we can write it this way. So the wavelength is inversely proportional to both the mass and the velocity. So does anybody want to guess what I'm going to say next? Something that I've said many, many times. Okay, yeah, momentum, that's true, but hold off on momentum. What is it that I always do whenever I say that something is proportional to something else? What's the next thing I always say after that? Yes. Okay, that's exactly right. Looks like we need a constant. Okay, so I don't like proportional signs. I like equal signs. Okay, so that means I have to add a constant in. And how do we find out the value of that constant? Anybody want to type in? What would we do to find out what the value? Test, exactly right. We just have to do a bunch of experiments, okay? So what we do is we take a known wavelength and a known mass and a known velocity, and we just see what the constant works out to be. And so that's exactly what Louis de Broglie did, was experimentally, he determined what the value of this constant was, and what he got was 6.63 times 10 to the negative 34, okay? Ah, hey, somebody is saying, hey, I recognize that number. Yes, that number is Planck's constant, okay? So instead of calling it K, we're going to call it H. So Louis de Broglie figured out that the proportionality constant in his equation was Planck's constant, okay? Now, I want you guys to think about this for a second, okay? So when we do experiments with light, we found out that light, the energy of the light, was proportional to frequency. And so we said, okay, so there must be some constant there. And so when we did a bunch of experiments, we found out that the proportionality constant was 6.63 times 10 to the negative 34. Now, when Louis de Broglie did his experiment, he got the exact same number for his constant. So this, what do you guys think? Is this an interesting coincidence? I mean, over here we've got light, which is very, very different from matter, right? I mean, matter is stuff that you can hold in your hand, but you can't hold light in your hand. So here we got these two different things, okay? We got two completely unrelated things. So on the left-hand side, we got light. On the right-hand side, we got matter. And when we do it, we find out that the proportionality constant is exactly the same for both of them. So what I suggest is let's ask this guy right here, What does he think about that?
Coincidence? I think not.
Could you guys hear the sound just now? Okay, good. All right, so yes, I agree with Bernie here. Coincidence? I think not, okay? So what this means is that light and matter must be connected in some way that we had never guessed before, okay? Because there's no way in the world that it can be a coincidence that the proportionality constant for light turns out to be the same as the proportionality constant for matter. That cannot be a coincidence. So there must be some connection between the two, something that we had never guessed was possible before. Okay, so let's do something. Tell you what, let's derive an equation. Let's derive the relationship between energy and matter. Okay, and so what the derivation we're about to do might very well be a question on our next test. So I trust that you guys are going to get out your notebooks and write this down. Okay, and also, I don't want to do it myself. I want one of you to do it. So let's see, who's online that I haven't picked on for a while? Ellie. Ellie, you're online. Can you turn on your microphone, Ellie? Do you have a microphone that you can turn on?
Yeah, I do.
Okay, good. All right, Ellie, I want you to do this derivation.
Okay.
I'll give you a little bit of help, but I want you to do it. Okay, so on the left side, we got E equals some constant times F, and on the right side, we got lambda equals some constant over mv. And experimentally, we've determined that they are the same constant, and we know that can't be a coincidence. So here, Ellie, what I want you to do is I want you to take E equals HF, and I want you to solve it for H. What would you get?
Okay, H equals E over F.
Okay, you guys agree with that? Okay. All right, now, Ellie, I want you to do the same thing on the right here. I want you to get H all by itself. Tell me what you get.
Okay, H equals lambda times mass times velocity.
You guys agree? Okay, good. Yep, I agree with that too. Okay, Ellie, now I want to somehow connect these. How would you recommend we do that?
Set them equal to each other.
Sounds good to me.
Yeah.
Okay, so if I've got something on the left side is equal to H and something on the right side is equal to H, well, what that tells me is the thing on the left side must be equal to the thing on the right side. So I agree with you there, Ellie. So it looks like E over F equals lambda mv. Okay, so now, Ellie, what I want you to do is solve for E. How are you gonna do that?
Multiply both sides by F.
Sounds good to me. Okay, there we go. Okay, now, let's take that F. Do you know any equations that relate F and C and lambda?
Lambda equals C over F.
Very good. So if we arrange that, then if we rearrange it, then we get F equals C over lambda. Okay, so we've replaced that. What would you recommend that we do next? We got a lambda on top, lambda on the bottom. What do you recommend we do with that?
Cancel out the lambdas.
Sounds good to me. Okay, good. Now, if matter were to get converted into energy, and if it were to travel as an electromagnetic wave, what would this V, the V here, what would that be equal to? What is the velocity of an electromagnetic wave?
It would be equal to C.
It would be equal to C. Guess what you just derived, Ellie?
Einstein's equation.
You just derived the most famous experiment, the most famous equation in all of physics. So congratulations, Ellie.
Oh, thank you.
You deserve a Nobel Prize for that.
Sounds good. I'll expect one next year when I come back.
Okay, that'll be good. Okay, you can turn off your mic now. Okay, so are you guys disappointed with how easy that was? Remember the other day I was talking about Einstein's Nobel Prize, and I told you that he didn't get the Nobel Prize because of E equals mc squared. He got the Nobel Prize because of his discovery of the answer to the photoelectric effect. It turns out that deriving E equals mc squared is actually disappointingly easy. Even Ellie can do it. Sorry about that, Ellie. I just couldn't resist. Okay. All right. So I would recommend you guys keep this written in your notes here, because you never know, this might be a question on our next test. Okay. Now, A little while ago, Josh was asking about momentum. He said that the book asked us some things about momentum, or they talked about momentum, and then we never really used it in the homework. So he says, what's the deal with that? Well, so here it is, okay? So Josh, since, yes, Aaron, or Jaron, you are right. That is where we're going, Jaron. We are going to get into the Heisenberg uncertainty principle here. Okay, so Josh, I want you to turn on your microphone for a minute. Can you do that?
Yes, I can.
Okay, good. All right, so I got a question here for you, Josh. Here's an electron just sitting here minding its own business, not bothering anybody, sitting still. Along comes a photon. That photon hits the electron. So the electron then starts moving away. Okay, it's absorbed some energy. Now the photon may or may not have given all of its energy to the electron. You know, it certainly gave some to the electron. Maybe it has some left over, maybe it doesn't. So Josh, do you see any problems here? Does this, you see, we might have just broken the laws of physics?
Well, if I'm thinking about it, shouldn't the photon bounce back? Or is it coming straight onto the electron?
Maybe it is, maybe it isn't, but let me rephrase the question. You remember this law of physics right here, right? What is this law of physics?
That the momentum before the collision is equal to the momentum after the collision?
Right, so we call that conservation of momentum, okay? So here, how much momentum did we have before the collision? Okay, so if we got m1, v1, m2, v2, so if this electron is sitting there motionless, how much momentum does it have?
0, and then it gains some after.
Yeah, so here comes a photon. Now the photon is moving, but the photon doesn't have any mass. So before the collision, our total momentum is 0.
Oh.
After the collision, we've got an electron that is now moving. It now has momentum. So what's the deal here? Did we just break the law of physics?
Yeah, man.
Yeah, so it looks like we can all go home, except that too late, we're already home. Now, Cohen has just pointed out that the photon lost energy, and that's true, okay? But if the photon doesn't have any mass, then it doesn't have any momentum. So before the crash, we had 0 momentum, and after the crash, we have non-zero momentum. So we either broke the laws of physics, or maybe we just didn't understand. Maybe there was a law of physics there that we didn't understand, okay? And it turns out that photons have momentum. And so this is called the Compton effect, actually, okay? So the book, they just told you that the momentum of photon is h over the lambda. They didn't tell you where it came from. So here are the steps on how to get it. I don't think I'm going to take the time to go through these because it's getting a little bit late. I don't want to make this class run more than an hour. So take a screenshot or something of what you see here. So if you start with E equals HF and do a little bit of algebra, and then replace E with mc squared, you'll find out that a photon has momentum. Even though it doesn't have mass, it has momentum, which is pretty weird. Pretty weird, okay? And the momentum of the photon, the equation for the momentum of the photon turns out to be the same as the equation for the momentum of matter, okay? If matter is a wave, okay, so Louis DeBroglie proved that, okay, so just do a little bit of algebra here. What you find is the momentum of matter, you know, like electron and proton and all that stuff, is equal to h over the wavelength of the matter. And so for matter and for photons, for light, the same equation will tell you what the momentum is, okay? So kind of weird, but that's the way it works. Okay, so that's pretty much all the new stuff that I'm going to give you today. Your homework is going to be problems 19 through 27. Don't forget to take the daily quiz. And so let me just open it up. Does anybody have a question? Okay, so Jaron. Jaron is saying that as we use photons to measure, we know the very act of observation changes the results. Okay, and that is, so what Jaron is talking about here is something that's called the Heisenberg uncertainty principle. I am not planning to talk about the Heisenberg uncertainty principle today, but I definitely plan to talk about it on Friday. So on Friday, we're going to talk about the implications of quantum mechanics, or maybe I should say the applications of quantum mechanics. So on Friday, we're going to talk about how quantum mechanics is actually used in real world devices that you use every single day. And Heisenberg uncertainty principle is going to be a big part of it. And Emmanuel is saying that yes, you learned in chemistry as well. All right, so Yasin wants to go back to the previous slide, as there is still time. Okay, so Yasin, here's the previous slide. Oh yeah, secret word. Okay, good point there. But before we get to the secret word there, so Yasin, do you have a specific question, or you just want to look at it so you can copy it down into your notes? Okay, you're just writing notes. Okay, so Emmanuel, seeing as how you were the one that picked the secret word, what would you like the secret word to be? Caesar? Okay, so C-E-A-S-E-R. Okay, yeah, too late, Jaron. Emmanuel beat you to it. Okay, so Caesar is our secret word for the day. Okay. All right, well, I think that we are good. Okay, so you were making a joke, but oh, okay, I gotcha. All right, I didn't get the joke at first, but I get it now. Okay, well, I think we're done. If I don't see any more questions popping up, I will go ahead and end the recording. So going once, going twice. So